Okay, this lecture is going to cover one of several flavors of transition state theory. We will do a few of these versions of this theory. It is, of course, extremely useful, and I'm going to cover a few that I think come up most often in applications. The one we're going to start with is the most familiar one in the hands of chemists, and that is the I-ring version of transition state theory, where we start from elementary statistical mechanics. So the idea in transition state theory is that you have reactants, and they are in equilibrium with a transition state. Is an entity, a species, if you want to think of it that way, but it's an intrinsically unstable, ephemeral species. So as soon as it gets reached, it continues on to products and never turns back. It's one of the key assumptions of transition state theory. So really, the theory makes these two assumptions there. The key assumptions in the theory are that we have an equilibrium between the reactants and the transition states, and that once we reach the transition state, we irreversibly go on to become products. So let's draw a little free energy diagram here to depict that. We have a free energy as a function of some reaction coordinate q, and I might have more to say about what that reaction coordinate is later in the class. Depends on how far we get with things. But then we have a free energy profile that looks something like this. Okay, so we start out with a low free energy region, which corresponds to the part of phase space where I still have intact reactants. And then we go over this barrier, and the barrier top is at location q double dagger. And so that, in a sense, is our transition state, everything that lives here at the top of the barrier. And the assumption is that these reactants are in equilibrium with the things that live up here at the top of this barrier. And to make those things well defined, we have to give this region a little width, and it's going to be completely arbitrary what width we choose. And fortunately, in the final analysis, that width will vanish entirely. But once a trajectory comes up here and crosses through this region, it just keeps on going and never turns back and becomes a long-lived product. Okay, so this is the basic assumption behind the theory, and what we're going to do now is to begin to formulate a rate expression. Okay, so the reaction rate is given by a frequency factor multiplied by a concentration of these transition states. Now, the concentration of transition states is the number of these entities in my system per volume. So this is a regular per volume concentration, and the frequency refers to if I know that I have an equilibrium population of these things and they have equilibrium properties, so they're moving along this reaction coordinate with a Boltzmann distributed velocity, then I can compute the frequency with which they escape out to the product side. Okay, so this is the frequency at which these transition state entities escape to the product side. All right? Now, in a sense, both of these two quantities are ill-defined. Okay, so we have these two ill-defined quantities, and this gave Guggenheim a lot of trouble, and he in turn gave I-ring a lot of trouble about the validity of the theory. But even though both the concentration and the frequency at which these transition states escape, these are both ill-defined things, their product is a well-defined rate. And so what we're going to do now is to begin to use the law of mass action and chemical equilibrium relations to construct expressions from statistical mechanics for this equilibrium constant that will tell us what the concentration of these transition states is when we know the concentration of the reactants. Okay, so this is where we start. We write down the usual mass action ratio. The usual one would not include this little factor here. Ignore that for the moment. So we've got a q double dagger divided by v. Now, the volume is the volume that would appear in the translational partition function. And when we divide by that volume, it completely vanishes from the calculations. We never really have to specify that volume at all. Remember that the translational, the overall partition function is a translation, rotation, vibration partition function all multiplied together times this Boltzmann factor for the 0-point energy. And I want to focus in on what's going on in here. So this translational partition function was the volume divided by 3 factors of the de Broglie wavelength, thermal de Broglie wavelength. When we divide by the volume just goes away, and we have those 3 factors of the de Broglie wavelength left over. Now we're going to have that happen for our transition state and for each of our reactants in the denominator. And so this is what gives you the appropriate units. If you think carefully, those units are entirely coming from the de Broglie wavelength factors. And then there's this other piece in here. Okay, so when I count up all these degrees of freedom for the reactants, then I count, the partition functions here are summing 1 per degree of freedom as you normally would. But for the transition states, we have one of the internal degrees of freedom is our reaction coordinate. It's not a vibration, it's not a translation, it's not a rotation, it's not clear exactly what it is, but it's clearly unstable. And so we think of it as an unstable vibrational mode. It has an imaginary frequency. If you do a harmonic approximation, we already covered that in one of the previous lectures. And so the basic idea now is that we're just going to locally, for lack of anything better to do with this, we're going to locally treat this as a translation along an internal coordinate. So it doesn't have a volume that we're dividing out, and yet we can treat it like a translational partition function. And that's why we get the width of the region that we're summing along divided by the thermal de Broglie wavelength for that degree of freedom. Now I should technically remember that that's the thermal de Broglie wavelength for the Q degree of freedom, which has a reduced mass and not an absolute mass of the molecule like the other thermal de Broglie wavelengths do. Okay, so for our thermal de Broglie wavelength along Q, we have this expression. This is our Planck's constant divided by the square root of 2 pi. There's the reduced mass along the reaction coordinate at the transition state, and this is Kb times T. Okay, so these are all of the things that go into that part of the calculation. Now what I want to do is to begin to think about how to compute the other piece. Okay, so the other piece of this is this frequency factor. And the frequency factor we can also get from equilibrium statistical mechanics. Okay, so what we're going to do here is we're going to say, well, the distance that I have to travel is delta Q, and I know the absolute average velocity with which I'm traveling, and now if I use a distance equals rate times time formula, I can get the frequency with which I will leave. But I only want to count those trajectories that are exiting out the right. Okay, so I'm only going to count half of the trajectories that are carrying me out of one of the 2 bounds, and I'm going to use the absolute average velocity evaluated at the transition state, and I'm going to divide by the width of that region. Okay, so this is the inverse time is the velocity divided by the distance. Okay, this is basically a distance equals rate times time calculation. All right, and now you can see here that this is a canonical average that we have to do, so we're going to have to do some integrals. And I can remind you of what calculations look like. So everyone has done these, I'm sure, in the class. But I've got a 1 over kBt. I've got a reduced mass. I've got a velocity along my reaction coordinate. And I've got my factor of 1/2. So this is basically my kinetic energy divided by kBt. And the thing that I'm averaging was the absolute velocity along my reaction coordinate, and I have to include that part of the partition function that doesn't cancel with other things. We've really canceled off a lot of stuff here. Okay, so I have to do a Gaussian integral in the denominator, and I won't go through the details on that. I'm sure you guys can all do it. 2 kBt divided by pi times mu q. Okay, so our generalized mass of our reaction coordinate is appearing here, and it's also appearing over here. Okay? And so it's kind of a part of both calculations. And so I maybe before I turn the page, I should just reiterate that this omits the unstable mode, the unstable vibrational mode at the transition state. So we're leaving that out of our partition sum. Okay, well now what we have to do is to put all these pieces together. And really, that is just a matter of multiplying this frequency factor that we derived by an expression for the concentration of the transition states. And we can do that by using the equilibrium constant and the frequency factor and multiply these by the concentrations of species A and B, right? So that these two things are the rate constant from transition state theory. Okay, so once we derive this, once we multiply all these pieces together, we're going to be finished. Okay, so KTST, this 1/2 of the average absolute velocity at the transition state divided by my delta Q. Okay, that's all the frequency factor. And then the other part is my equilibrium constant. That was delta Q divided by the thermal de Broglie wavelength, like this. Then we have all of the regular partition functions, like this. Okay, and let's go ahead and start crossing things off. Okay, so you're probably already seeing that there's a lot of cancellation is about to happen here. This cancels with this. And fill in some of these details. I'm going to write the result that we got for the integral that we did on the previous page. Okay, there's that reduced mass again. Then this part in the denominator of the denominator is going to come up and be in the numerator. So let me go ahead and write that in. Okay, and we are gradually cleaning up our mess here. That cancels with that, and we get some more cancellation. The factors of pi also cancel. The factors of kBt are there twice, so they're going to remain. The factor of h is going to come out. The factors of 2, they cancel as well, and we end up with kBt over h times q double dagger over v, qa over v, qb over v. All right, so there are a few things that I want to call your attention to about this formula. Of course, one thing that's very useful is that our mass of Q vanishes. And this is great. We didn't want to have to compute that, okay? The other thing is that delta Q vanishes. Again, we didn't want to have to specify this completely arbitrary quantity, and so it's great that it vanished from the formula. One of the last things I want to point out here is that each degree of freedom carried an h to the minus 1 from the partition function. Now, there is one left downstairs because we treated that degree of freedom separately. Okay, now this is an important point. In the harmonic transition state theory, if we treat everything classically, as done by, for example, the Vineyard formulation of transition state theory, where you just end up with frequencies and no h's, the extra 1 over h is going to be buried within the reactant partition function. And so the value of h doesn't really matter. Okay, this is an important point to remember. It does matter for quantum mechanical vibrations. It appears in that vibrational partition function. But everywhere else, whatever value of h you put in is going to completely vanish from the formula. It looks like it's important, but it's actually not, right? So this thing, of course, you would see this prefactor, if I used a strange value of h, would give me a strange value of this prefactor. But I would get an equally strange value of this ratio because there is one extra factor of h buried in here through the omission of 1 degree of freedom. Okay, last little bit here. I want to talk about why transition state theory works. Okay, and by work, I should qualify this, that it really works quite well for reactions in high pressure gases. You know, as you go to very low pressures, you need to use RRKM theory. As you go to condensed phases, sometimes you need to use something like a Grody-Hines theory or a Kramers theory. But it has a remarkable range of validity for things that are in high pressure gases. And I think that it's useful to understand really why it works as well as it does. Okay, so I'm going to remind you of how we construct in practice this reaction coordinate. Remember that we got this reaction coordinate by defining Q as the displacement in mass-weighted coordinates dotted into the unstable vibrational mode. Okay, this is usually how you construct this thing. Now that means that if I look at my local potential energy surface, I pass through a barrier here at the location corresponding to my transition state. Now the actual numerical value of Q, according to this definition, this is delta X as a displacement from that transition state location in the full dimensional space, free in dimensions of my molecule. So that is going to actually coincide with 0 in this particular case. But that really doesn't matter. What matters is that we have an unstable mode from a vibrational mode analysis. So locally, the vibrational modes are all separable. They're all dynamically separable, which is to say that when I move along one, I'm not interfering with the other one. That was the purpose of diagonalizing that mass-weighted Hessian, was to make that happen. To find the modes is to find the locally separable motions. Okay, so if I draw a picture now of my expanded phase space and think about variable q and its velocity, I can now imagine what trajectories look like. The trajectories that go in the opposite direction. Okay, so these are the ones that were discounted because of that factor of 1/2. So within the quadratic approximation, you see that transition state theory is accounting for exactly those trajectories that actually make a positive contribution to the rate. Okay, so these were the wrong way, and it doesn't get counted. These were going the right direction. They have a positive velocity as they cross through the transition state, and they are getting counted.